Avikash Naidu, Felicia Nasrun, Joe Wickens, Nic Zwager, and Tony Z allowed the University of Auckland Engineering Department to show this video to future Part 1 students as an example of a statics experiment.
For our first friction experiment, we have decided to test which surface would be the best to use as a cutting board from a range of stone, wood, acrylic, and plastic surfaces. Therefore, their friction coefficients being our independent variable, and the angle at which a block of cheese would slide on these different surfaces being our dependent variable. Now we tried to minimize errors by keeping every variable the same, except for the material that the block of cheese was sliding on, so that we can obtain the angle just prior to the cheese block sliding. So the setup of our experiment, as you can see here, is having this long table, which we kept the same throughout the whole experiment, and it is inclined on one end by a pile of magazines. And we varied the surface that the block of cheese is sliding off each time.
And the cheese tips roughly around this angle. Part 3, acrylic. Tips around this angle here. Friction experiment 4, plastic graphic sheet, tips at very low angle compared to the rest.
We took some measurements and formed a free body diagram in order to obtain the angle just prior to the cheese sliding off. Referring to our free body diagram of the experiment, we must first take a closer look at the weight force of the block of cheese on the right here. The x component of this weight force is equal to the mass multiplied by the acceleration due to gravity multiplied by the sine of the angle. This means that at the point of motion, friction must be equal to the sine part. As for the y component of the weight force, the normal force going up is in fact equal to the cos part here, and that is the component of the weight force that is directed into the surface. Now, to cause sliding of the cheese block, the friction force is dependent on the roughness of the surface, therefore the coefficient of friction, and the normal force, so that we get the equation mu is equal to friction force over normal force. And when we substitute the sine and cos parts, we get that angle is equal to the inverse of tan of mu. We can then use this equation to calculate the coefficient of friction of each of the surfaces. We firstly worked out what the angle of the slope is for each surface based on the measurements we took. Rearranging the relationship I described earlier, mu is simply equal to the tan of the angle, so that we can calculate the coefficient of friction of each surface type. The result is that acrylic and wooden surfaces had the highest coefficients of friction, and the plastic graphic sheet had the lowest. Hence, we can conclude that the acrylic and wooden chopping board are the most suitable surfaces due to their greater coefficient of friction, meaning that less sliding will occur, as we saw with the block of cheese, and that these boards will be safer to use in terms of health and safety. Our second experiment involved trusses, and we aimed to determine how the number of trusses influence the amount of force that the system can withstand. This means our independent variable was the number of trusses, and the dependent variable was the maximum amount of weight that can be supported without breaking the truss system. The method we used to do this experiment was, we took a truss system and we placed it on two corners over a gap. Then we loaded sand into a bucket attached to the center of the truss, until the truss eventually broke from the downwards force. We weighed the mass of the fully loaded bucket after the truss collapsed, assuming that this was the weight at which the truss would collapse. These were the bridge shapes that we came up with, and we numbered them from 0 to 5. This next slide shows the initial Lego bridge that was designed, but the Lego bridge itself would flex too much and would take an unrealistic amount of weight before giving out. So instead, we went with constructing the bridges out of skewers and hot glue. Since they weren't overly strong, we could break them with weights that we could find available around the house. This is a quick time-lapse of construction of the bridge using skewers and hot glue, and we ended up with some final designs of the trusses. As for the experimental setup, this was how the bridge was supported, and we ended up adding clamps to each end to support and ensure that the bridge didn't collapse through the gap under the bridge. To add weight, we hung a bucket from a carabiner clip as shown here, and gradually added soil and/or water. This would ensure more accurate results, as we could then have a better control over the amount of weight added. The scale we used only worked if someone stood on them, and so Nic's dad had to weigh himself prior to the experiment and did not eat nor drink during the duration of the experiment. Measurements were then taken by weighing Nic's dad, who was 86.2 kilograms at the time, with the bucket and the clips. Now the weight withheld by the bridge was calculated by minusing 86.2 kilograms off the total weight. So here's how the experiment went for each of the trusses from 0 all the way to 5 trusses. For the truss shapes we designed here, the pink or purple lines represent where we placed the bucket for each truss and how that affected the splitting of the forces among the joints on the trusses. When we take a closer look at the free body diagram, the weight force going down at the joint causes tension on the bottom of the truss and compression at the top of the truss. The tension on the bottom is caused by it bending downwards and the bottom fibers becoming elongated, whereas the fibers of the skewer at the top get shorter. The skewers broke on the tension surface because the tension fibers of the timber or the wood are splintered. As for our results, as the number of trusses increased, the weight at which the truss system can withstand also increased, producing a general linear trend. The only point that is a clear outlier of this general linear trend is our first data point, where the number of trusses equals 0, as you can see here. The reason that our first point at 0 is considerably above the trend line is because the wood itself has an axial tangential force, and so the strain on the wood can apply a force upwards using its strands. And so as depicted from our results, there is a linear relationship between the number of trusses and the weight it can hold, and when n is equal to 0, the force is equal to the axial tensile strength. Some factors to consider are the material and thickness used in the system and the strength of the pins used in the experiment due to the glue. Glue may have a different influence as it is a different substance to the wood. So in order to link the experiment to theories we have learned, the trusses broke in tension and broke from the bottom because of bending moment. We used moment equations to obtain vertical reaction forces, VA and VB. The edges of the trusses were held down in order to obtain maximum values of VA and VB, as the system would fall apart before attaining maximum capacity if VA and VB were not high enough. Instead, we would just be testing how strong the glue was. Some assumptions we made included the force that is used to break the truss system is a value just above the value for static equilibrium for the truss system. We also assumed that the self-weight of the skewers was negligible. In conclusion, the amount of weight able to be supported by the truss system increased with increasing number of trusses. This is because having more members in the system means that the weight force can be distributed over the whole truss system, so that more weight is able to be placed on the truss at one point before it breaks. Thank you for listening. We hope you're having a great day and are staying safe.